Okay, so welcome back, everybody. This afternoon we have Sebastian Mizera, who will tell us about Feynman Polytopes and orthogonal geometry of UV and Lyra divergences.
All right, well, thank you so much, and thank you for the invitation to this workshop. So today I wanted to talk about this recent paper that appeared on the archive together with two of my fantastic collaborators, Nima Kanyamet, who's in the audience, as well as Aaron Hillman, who's a grad student at the university. And actually, the organizers of this workshop asked me to be very pedagogical and make sure that everyone understands everything. So for this reason, what I'm actually going to talk about today is the appendix of this paper, in which we go slowly through all the math, and then I will sort of put under the rug all the physics. So there's no physics requirement to the purposes of this talk. However, what I will mention is this physics motivation here, which says that the predictions for the particle physics experiments are usually computed with the class of integrals, which are called the Feynman integrals. Okay, for the purposes of this talk, you can think of a Feynman integral as an integral which depends on some parameter epsilon, which we want to take very small, and also a bunch of other parameters. And then the problem that we wanted to tackle in this talk is a Laurent expansion of this function as epsilon equals to 0. Okay? So in principle, what we wanted to be able to determine is first of all the degree of the divergence, so the leading coefficient of the sum, and also compute consistently these expanded coefficients of the expansion. Okay, so the in principle and the sort of theme of this talk is that expansion is a topic in tropical geometry. Okay? So the plan for the talk is going to be very simple. What we're going to do is we're going to start with toy models. And then slowly we'll move on to the full Feynman integrals. So hopefully by the end of the talk we'll see some Feynman integrals on the board. Okay. So speaking about the toy models, let's consider this integral in here. So this integral I here depends on 3 parameters. So for the purposes of this talk, you can think of these parameters as all being real and positive, and is defined as an integral from 0 to infinity of x and y, and the dependence of the parameter is in the exponents a, b, and c here. Of course, this integral you can do very easily. You can just put it on a computer or even evaluate it by hand, and it gives you this collection of the gamma functions. Okay? So there's poles as a goes to 0, b goes to 0, and this combination goes to 0, as well as zeros when c goes to 0. Okay? But the problem that we wanted to consider is what happens as we send some of those parameters to vanish. So let's say we come up with this epsilon here, and we will scale a and b to be very small, keeping c constant and constant. Okay? As you can read off easily from this answer, this is going to behave as 1 over epsilon squared times ab plus some corrections, like this. Okay, and the question that we wanted to ask in this talk is sort of the simplest example of this phenomenon in here, in which we wanted to ask how to obtain this thing directly. So directly meaning without the computation of the full integral, which might be very difficult. As you can see already at this example, the difficulty in the type of function that we get drops drastically with the leading coefficient. Okay, so we're going to start with a class of functions, which is a generalization of the hypergeometric functions. And it looks as follows. So consider the following generalization. We're going to have an integral that depends on the vector of numbers a, c, and possibly some other parameters. It's going to be an integral, just like this one, over the positive values in d dimensions of variables which I will just call x. Okay? put here x to some powers. So we isolate x to the minus 1, which gives us a logarithmic measure with this part, and some independence of the parameters a, which is the analog of the parameters in there, as in this example. And then we'll also allow a number of polynomials. Okay, so these polynomials here can in principle depend on some other parameters, and we can just think of them as being some expansion with some and for the purposes of this talk, we'll be thinking about these betas here as positive parameters, and these are the parameters that can enter in this betas here. Okay, so what we'll study is the case in which those parameters are fixed and positive, and then we'll modify the a's and c's, these exponents in here. Okay. There's also a more complicated version of this kind of integrals in which you allow betas to be positive and negative, and then in principle you have to worry about the types of singularities that Simon was talking about yesterday, these sort of lambda singularities. Okay? But for now, the only divergences that this integral can have, because this function is manifestly its only positive coefficients, can only occur at the boundaries of the integration, so as x equals to 0 or infinity. Okay, so it's very convenient at this stage to do a change of variables from x's to what I call lowercase x, which are just related to the original ones by the logarithmic up. And the effect that this has is that all the singularities in the integration domain are now at infinity, as this lowercase x goes to plus or minus infinity. This gives us a mapping of all the divergences at infinity in the real space of the divergences. Okay, so now what we're going to be interested in, because we wanted to study what happens at infinity, we're going to be interested in the leading behavior of the integrand. Okay, so the leading behavior is going to be in terms of the lowercase variables. We have the integrand that looks something like this, some product of i's, of the j's, minus c. Okay, so, and then we're going to say that this at infinity looks like e to the trop, where trop is some function of its parameters, a's and c's, and x's, of course. Okay. So trop is going to be the tropicalization of this integrand, and it's given by simply a of x, where dot means a contraction of these vectors, minus okay. And now, because this thing can be a combination of many monomials in here, some polynomial, what we're interested in is only the maximum one that survives in a given direction at infinity. Something like this. Okay, so the max here is taken over all monomials. Okay, so let me notice that trop is of course a piecewise linear function. piecewise linear in the integration variables x. Okay. And what it also tells us is that the integration space, which in these variables is r to the d, is styled by cones, a set of cones, which I will call CV. So each CV can be understood as a convex hull of a given number of points. Okay? So the standard picture here is that if we're looking in this integration space R to the D, there are some directions, and there are these extremal rays. Each cone has something like this. Okay? And to each of them, we can associate these extremal rays. Okay? So far so good. So at this stage, let me just come back to the previous example, and let's do it maybe here. Okay, so recall that in the previous example, we had this integral dependent on a, b, and c. And now, in terms of the integration variables, now the lowercase x's and y's, say, we have the integral that looks like this. Here we have x, y, and minus c. Okay? In this case, it's very easy to write down the trop function. The trop is simply equal to ax plus by, and then we exchange this by max. 0, x, y. Okay, so the picture that we get is in the integration domain, x and y. The trop is a piecewise linear function, and it depends which exact function we get. It depends if x is positive, negative, or if x is larger or equal to 0. So there are these special directions, x equals y, x equals 0, and y equals 0. Okay, and then what we want to consider is what happens as we tune these parameters here to be very small. Okay, so of course, when x and y are both negative, it means that max of this is 0. So in the strict limit, as epsilon goes to 0, the value of the trop function here is 0. Okay, likewise, this always tends to 0. So likewise, in the other chambers, we'll get minus c, minus cy in here, and minus cx in here. Okay. So now we understand where the divergence comes from, because recall that we're approximating our integrand with e to the trop. In this direction, we get e to the 0, which means that in this direction, the integrand is no longer suppressed. And this is precisely where the divergence comes from as we set epsilon to 0. Okay, more generally, we can evaluate this trop in different cones. And there are three options. Either the trop is positive, 0, or negative. Because we're approximating our integral by e to the trop, the integrand by e to the trop, whenever it's negative, it means that we get a finite contribution from this direction as we tune epsilon goes to 0. When it's 0, like in this case, it means that there's a divergence. And in physics, we would call this a marginal divergence. Okay, meaning that this is the least amount of divergence we can get to still get 1 over epsilon poles from this thing. And when trop is being positive, it also gives us a divergence, but in a sense worse. Okay. Very good. Is there any question about this simple example?
If I want to get the second or third term, do we have similar techniques like this, like the tropical?
Yes, I want to talk about this today,
Okay, sorry.
but we will work on it.
Yeah. Okay.
Yes, so in principle, the fact that this cone, we have a cone here, and the fact that it was a two-dimensional cone, it tells you that we had this kind of divergence in two directions. So this in particular tells us that the integrand will have to diverge as 1 over epsilon squared with some function here. And what we were interested in is we've already nailed down what the degree of the divergence is. And I want to also understand what is this function. So, okay, so now let's distinguish between two cases. So just to make sure, this column in here is what I call CV on the Phoenix board. And it's called C sub V because to those of you who are familiar with normal fans, it's going to be dual to a normal fan of the polytope. Okay, so now we can distinguish between two cases. So the case 1 is in which the dimension of this cone is exactly the dimension of the integral of the number of integration parameters. So it's a top dimensional contribution. Okay. So for this purpose, as I said, the cone in general will be spanned by many. Actually, let me write a parameterization right now. So it's CV is going to be can be parameterized by a positive linear span of some extremal rays. So there will be some extremal rays in here. That'll be 1, that'll be 2, all the way up to something. Okay, so this is the positive parameterization, so all the lambdas are positive. Okay. And now, of course, there could be more extremal rays than the dimension, but we can always triangulate each cone and triangulate it into being simplicial. So for the purposes of studying the contributions from each of them, we can just assume that CV is simplicial in the first place, and otherwise we just have the sum over simplicial contributions. Okay, so let's assume that the cone is simplicial, and then what we can do is simply evaluate the contribution in this tropical approximation to the integral coming from a given simplicial cone. Okay, this is simply done by a change of variables. So we change the variables. We write them first. So we change the variables to these lambdas. Okay, lambdas were the ones that we were generating the cone. And they're already positive, so I'm integrating over R plus to a given power. Okay. And we're considering top dimensional cone, so the number of integrations is d. Okay, so because I'm changing the variables from the x's to the lambdas, I have to pay a price of this geotropic. Okay, but now simply the integrand can be already approximated, at least the divergent contribution to the integrand can be approximated by this function here. Okay, so we're evaluating a contribution in a given cone, and then along this given cone, this is dominated by this, the integrand is dominated by this contribution here. Okay. So you can simply put this integral here. It's very simple because everything is linear. And you will get -1 to d. Then you copy this permanent.
So I thought these W's are they're constant. No? We understand W function.
The W's are the extremal rays.
But they're fixed.
They're fixed,
So
and
then what do you mean by trop of a fixed vector?
I mean just the value of the Trop function evaluated in this direction.
I see. Yeah.
And then
Yes,
then you can worry about the normalization.
That's fine.
But the normalization
It's clear.
drops out. One thing to point out is that we're already interested in the specific rays which are divergent, meaning that all these trop are proportional to epsilon. And they go to 0 as a single power of epsilon. And this means that this contribution here is proportional to 1 over epsilon to the power of d. Okay? In principle, it's some number. I just compute the number. This. And this is often what we call the volume of this column. This is, in a sense, a definition of the volume of this column. Okay, so we just went through the example in which the dimension of the cone was equal to the dimension of the integration. And now, what we're going to do next is the other sort of physically more interesting in our application case in which the dimension of the cone is less than d. So let's do it here. I guess I should have applied this to this example. If we apply this to this example that I just erased, we would see that everything goes like 1 over epsilon squared, and that the value of the Trop function in this direction and this direction would be as the a. Okay. And now let's move on to the more interesting case of when the dimension of the dual cone is some m, which in principle could be smaller than d. Okay, so it's a higher dimensional distribution. This means that we can parameterize it Cf. X can be parameterized as the positive span of the extremal vectors, extremal rays in here. Okay, so the same picture as before, but now we can have the other directions which are orthogonal. Okay, so we have some orthogonal directions in here. Let me call them W bar, and it's actually up to you how you parameterize the orthogonal directions. The dependence will be dropped out for the final formula. Okay, so in this formula here, the lambdas, alphas are positive. Okay, so we're going in the direction of this cone, but these guys can have any sample. The response. Okay, but once again, we can assume that this cone here is simplicial. If it's not, then it would be a sum over simplicial cones. So in this case, we can evaluate the contribution from this direction in the integration space using a very similar formula. Okay, so once again, this simplicial case is when the integral in this direction of this cone is equal to in principle, we have m dimensions. These are the extremal rays generating the cone. There are the orthogonal ones. Here. So this is the Jacobian with the change of variables. Here, once again, we change the variables to the lambdas, which are positive. And then in this direction, you need to be dropped. But now at this stage, we also have the orthogonal directions, which we can just integrate over the r to some power, to the power of the dimension. Okay, and once again, here we have the integration over the lambda bars, and we have this integral here. And then in principle, we have the other polynomials. And then of course, since we're already approximating our integrals as these lambdas go to infinity, this is where this integral is being dominated, it means that we can in principle drop the corresponding monomials from this piece. So here we can drop the subleading monomials. Okay. So this factor, as before, is what we can call the volume of the column. And this is the rest. It's some coefficient that we just need to compute. Okay. The rest. So we could J sub f. Okay. At this stage, someone can ask about the quotation marks. The quotation marks are here because the definition of this volume actually still depends on this Jacobian. Okay, so that means that this individually and this individually are not well defined, but their product is. Individually, they depend on the choice of the directions. You can show that in the product, these directions drop out. Okay, so this leads us to the following theorem. Okay, so the theorem is that the result is that the integral, the family of integrals that we've seen before, that can be approximated to the leading order as the product of these volumes times the corresponding coefficients plus something. Okay, so here the sum is going to be over the maximal dimensional count CF, on which the drop is still 0, or when we leave the epsilon dependence, it's still proportional to epsilon. So we call the dimension of this, in this case, m. So the sum here is over all m-dimensional columns is weighted through this volume. The volume factor itself goes as 1 over epsilon m, and then it's weighted with some coefficients.
Can I ask a question? The original setup in the beginning, so you had these exponents a and c,
Yeah.
and all you allowed is to multiply one coordinate by an epsilon or not.
No, you can take an arbitrary for each a and c. You can take them at different rates to 0.
So I can epsilon squared, epsilon to the 7th.
Oh no, sorry.
So what are the allowed? What am I allowed to do with epsilon?
Oh, a subset of a's and c's can go as epsilon or not.
Okay, so you only allow 0, 1 vectors at the power of epsilon.
Yeah.
If I wanted, there could be, but this should generalize to a situation where I take epsilon to the 7, epsilon cubed, and so on. There should be a version.
Yes.
Okay. But this you have not yet done.
We have not So this epsilon has a particular physical mean, and in Feynman integrals we only encounter these 0, 1 scalings.
I see.
Okay, is there any other question? I think that we perhaps mentioned something that probably to many of you is obvious, is that there is a one-to-one map between the tropical space and the polytope. This polytope is what, when applied to Feynman integrals, we call the Feynman polytope. And the polytope itself is just the vector A and the Minkowski sum over CJs and the Newton polytopes of each of these. Okay, so on this Newton polytope, it has some vertices, it has some faces, and the dimension n cone is dual to a codimension n facet. That's why I labeled that. Sorry, I should have face. Okay, so we can briefly apply it to the previous example, in which we get the x and y with these extremal rays going in this direction, and this direction. Okay, so then the Newton polytope, let me remind you that the P polynomial, there was only one, and in this case it was very simple, it was just 1 plus x plus y. So the Newton polytope is a triangle, and it's shifted by here. I can write it as this. So then this cone, which I call CV, is dual to this vertex here.
You mentioned the word tropical space.
The tropical space.
So there's a one-to-one map between polytopes and tropical space?
The tropical function.
Oh, the tropical function.
Yes. So this was supposed to be an example.
Yes.
So let's actually, maybe you thought it's going to clarify things, let's put labels here. Okay? So for example, this tropical function had this direction in here, which is the cone that I call CV. It's a two-dimensional cone. It's characterized by these extremal rays, W1 and W2. Okay? So for example, W1, in this case, if you wanted to plug the numbers, it would be the vector like this. And the other one would be this vector. Okay? So in this case, we can apply this special case of this formula, in which it would tell you that this theorem would tell you that the I to leading order is equal to the determinant of this treated as a matrix, and then the value of the Trop function along one of them and along the second. Okay? So then this determinant is just +1. And then the value of the Trop function in here is going to be epsilon times A, minus epsilon times A, and here's minus epsilon times C. So this tells us that the leading order, this I behaves like 1 over epsilon squared A B. Okay. Okay, very good. So now with this technology, we can start talking about Feynman integrals.
So if PJ is analytic function,
Yes.
Do you still do similar things, or it has to be a polynomial?
Yeah, you can generalize it to probably, you can, like, you want to put some more complicated dependency here. We have not done that, but I'm sure you can do it. Okay, so next up, the Feynman integrals. So the definition of a Feynman integral is that it's an integral associated to a graph. So let me run an example graph in parallel. Example of the graph could be this one here. Okay. It has a given number of external legs and internal edges. And then to each of the internal edges, I will assign the so-called Schrödinger parameter. You can think of a Schrödinger parameter as the length of this edge, which can go from 0 to infinity. Okay, so to associate it to a given integral like this, given diagram like this, I have an integral. So the integral is over all the Schrödinger parameters here, where EG is the number of edges in this diagram. The internal edges, so in this case we have 3 edges, 1, 2, 3. And it turns out that there's a projective invariance which allows you to set the value of one edge to be is equal to 1. Okay, so in this case we could set that alpha 3 to be 1. Okay, and then in this integrand we'll encounter two polynomials, U and F. These are the so-called semantic polynomials that you've seen in Claudius and Simon's lectures yesterday. And they're raised to some integer powers. Okay. Then up front, we also have the gamma function normalization with d of g, which is the so-called degree of divergence. Which is equal to the number of the edges minus the number of loops. This is the space-time dimension, which we live in 4 space-time dimensions. And L is the number of loops, which is the first Betti number of the diagram. In this case, we have 1 loop. Okay, so I think you've seen those definitions yesterday, but let me remind you. These two polynomials, the so-called semantic polynomials. Okay, the first of which, U sub g, is given as a sum over all spanning trees P that you can obtain from the original diagram by removing a certain number of edges. So you have a diagram that has L loops. It of course you have to remove L edges to obtain a tree. Okay? And then in the sum here you put a product of all the edges that you have to remove from G to obtain a given spanning tree. Okay, so let's do this example. Let's call this diagram the triangle diagram. Then U of the triangle diagram is you have to enumerate all the spanning trees. Okay? We have something like this. When we remove this edge, this gives you the product of all the Schrödinger parameters of the removed edges, which is alpha 1 in this case. Then you can also have this diagram and this one. Okay? All of these are trees. In this case, we remove the first edge, so we have alpha 1. In this case, we remove the second edge, alpha 2. And in this case, we remove the first edge, which is alpha 3. Okay? So, on top of that, we also have the other semantic polynomial, which is defined similarly. And I think you've seen the full definition already. I'm going to quote right now only the so-called massless case. Okay, so massless case means that physically you can think of these particles associated to these lines as being massless. Okay, in this case, the definition is that we sum over all spanning two trees. Each two tree is a union of two trees, disjoint union of two trees. We call them ES and ES bar, where S is the set of the external legs that is attached to this tree. Okay. To each of them, I'm going to associate the Schrödinger parameters that we have to remove to obtain these trees. Okay, can you see? Okay, and I'm going to multiply it with some parameter. Okay, you can think of this parameter as being positive or 0, and this parameter is going to be 0 here. Only if a given tree looks like this when it's attached to a single edge. So only if ES or ES bar looks like a single edge. Okay, so to make it more clear, let me apply it to this diagram. In this case, we have the F of the triangle. Now we have to remove two edges to go from a one-loop diagram to something that is a disjoint union of the trees. Okay, the simplest example is this thing, where I've removed the edges 1 and 2, these two, and I have two trees, ES and ES bar. Okay, so associated to these guys, I will have some function. Physically, it's the momentum that flows between these two diagrams and alpha 1 and another. Okay, in principle, I could have also removed, say, this edge and this edge to obtain a diagram like this, say. Okay, but in this diagram, we have one of these dangerous trees in which we set the coefficient of that to be 0. Okay, so this does not contribute, but likewise this does not contribute. Okay. Okay, so now in the final step, what we can do is we can apply this definition to our diagram. Okay, after we do this, we find that the I of the triangle, now we have two integrals from 0 to infinity. Oops. Okay, 0 to infinity. They're called alpha 1 and alpha 2. And this. Then we have u polynomial to some power, this guy, and the f polynomial to some power. And we've already set the last edge to be 1, so this polynomial is in fact alpha 1 plus alpha 2 plus 1. If you work out the exponents, you will find that this is related in the spacetime dimension d. To this exponent. The line is here. Here, this one. Okay, and this in fact is the example of the toy model that we've seen of the first. Okay, we have two integrals, alpha 1 and alpha 2. Alpha 1 is raised to some power, alpha 2 is raised to some power, and then we have a polynomial which is 1 plus alpha 1 plus alpha 2. So this, in fact, is our toy model. Okay, so yes.
But if your graph consists of one point and just one leg, f will vanish, but will u vanish? One point and one leg. Yeah. What would u be?
Oh, so it's never possible. U is always a spanning tree. So it always is for a given number of vertices, it is to connect all of them.
Oh no, I mean you start with G being
Okay.
the trivial leg.
Well, for this edge case you can define it however you want because it does not appear in physics. Oh. Well, in this case there's no intervals. But yeah, that's a good question. Yeah, in the case when G is a tree itself, for example, something like this, we will define U of this to be 1. Okay, so this means that in fact the toy model that we've been studying from the beginning was an example of a Feynman integral, and now we know how to compute the value of this Feynman integral when epsilon equals to 0. Epsilon was related to the space-time dimension, this relation. Okay, but there's something special about Feynman integrals because they're attached to the given graph G. Okay, this means that not only we can study the asymptotics of this integral as epsilon goes to 0, but we can also attach a physical meaning which is related to the diagrammatics of these G's. Okay, so let me just flash you one of the results. The result, to understand the result, we need to give a couple of definitions. First of all, we have the notion of the subdiagram. So subdiagram gamma is just going to be some collection of edges and the relations that descends from the original graph. So for example, we have this guy, which is the edge alpha 1 from this original graph. Okay, another example is this. And this. Okay. And now we have the notion of the graph contraction, which means we take every connected component of the graph gamma and then we collapse it to a point. So in this case, when we started with G, contracted with gamma, for this edge, we just contracted to a point, which means we end up with this diagram. Okay, we're up to 2 and up to 3. And so on and so on. Okay, so here's the conjecture and claim. When you apply this tropical method to Feynman integrals, what you find is that the base of any Feynman integral type G, we usually take G to be connected diagram. They are classified in bijection with by gammas, all these subdiagrams. The gammas start to be connected. Okay, and with this, the second part of the claim is that the trough function associated with the given that G can be written, actually you can write it, here. G can be written as two cases, either D and G mod gamma. We call that D was this combination which counts the number of edges minus the number of loops, and it's d over 2. So it's either this if the G mod gamma doesn't depend on any squared. This does not appear. In other words, when f of G mod gamma is 0. Or minus d gamma follows. Okay, so it means that in the special case of the Feynman integrals, we can evaluate this function, but actually it turns out to also a connection with this diagrammatic description of the
Let me try to paraphrase this in possibly in a combinatorial language. So, so these polytopes are generalized permutahedra. So the normal directions of the facets are 0, 1 vectors, and this is a submodular function. True or false?
I'm not sure if all the vectors are 0 and 1s.
But they correspond to subdiagrams. So these are the subsets of the edges.
Oh, yes.
So on a generalized permutahedron, all the facet normals are 0, 1. And the facet inequalities are such a linear form is less or equal something, where something is a submodular function.
Yeah, they're all 0, 1, but the point is that we know what the zeros and the one. I mean, not just the directions, also the right-hand side of the inequalities
Yeah,
are characterized in terms
but this
of.
right-hand side is a submodular function. It's a submodular function.
It's definitely yes. The thing is to figure out exactly which inequalities you are changing for precisely which set of subgraphs correspond to shutting off momentum going to the infrared. It's a very simple rule, but it's not a trivial rule.
And I should mention that these kind of Newton polytopes of this U and F functions have been studied in the other cases in which the edges are massive by multiple people, including Schultka and Borinsky and collaborators. Okay, but for our applications, we're mostly interested in the massless cases, which in the physics language they give us the infrared singularities of Feynman integrals. Okay, so perhaps let me, in the final couple of minutes, let me just close with an example of this applied to our favorite diagram here. Okay, so in here we have the subdiagrams are each individual edge. So we have the edge alpha 1, which we've already seen. Then we can obtain alpha 2, alpha 3. And then we can also have these kind of edges, these kind of subdiagrams, but I'm gonna skip them. And in those cases, we can go through the list of G mod gammas. So once again, associated to this edge with the contraction, which gives us this G mod gamma. In which case this is alpha 2, alpha 3. In this case, we have, so this is a list. In this case, we have contracting alpha 2, which gives us this. Okay. And in this case, we're contracting alpha 3, which gives us this. Okay. So let's just apply these definitions one by one. Okay. In the first case, we have this diagram by itself does not depend on any scale. In other words, the f of G mod gamma of this diagram is 0, which means we're interested in this option here. So we call it d of G. Let's equal to this one to D. And we're interested in physics in 4 dimensions, which means that this is 2. Okay? This means that associated to this diagram, we have d of g mod gamma, which is the number of edges here is 2 minus the number of loops, which is 1 times 2, we have 0. Okay? This tells us that in space there's going to be some direction characterized by gamma 1. Okay, along which the trop is equal to 0. Okay, then associated to this, we have the same diagram. So this would be d of g gamma 2 is equal to 0 as well by the symmetry. Okay, so there's going to be some direction in which the trop is equal to 0 as well. Since trop was piecewise linear, it tells us that in this direction, trop has to be 0. Okay, and in addition to that, you could worry about this diagram here. But this diagram here has f of g mod gamma of this diagram is non-zero. That's because, well, you can write with this, it's equal to this. Okay, that's because we can obtain the span of the tree up here. So this means that we're supposed to apply this definition otherwise. And we're just computing the minus d of gamma 3. Okay, gamma 3 is a single edge, so it has 1 number of edges, and the number of loops is 0. Okay, so that tells us that there's some third direction in here, along which trop is equal to minus 1. So in this direction, everything is suppressed. In this direction, things diverge, and this gives us a combinatorial realization of the same tropical function that we've seen at the beginning. Okay, so with that, let me thank you for your attention.
So there are some more questions?
Can you recover the tropical function, like 1 over epsilon squared AB, from this? Or, sorry, not the tropical function, the coefficient at the end, like 1 over epsilon squared AB.
Yes. So everything in the end, applied to different integrals is purely combinatorial. So you don't have to write integrals in the first place, you can just obtain this. So in this sense, the only thing we need to know is to recover, say, the trop function. You need to know the values of the trop function from each ray. You need to know the adjacency of each ray. And from these facts, that the trop function is piecewise linear, this allows you to recover the full function.
Great, thanks.
And I have not talked about the adjacency. We can also, you can describe it. I mean, not about. Yes.
Sorry if I missed this, but did we cover the higher leading terms?
Higher?
Like the later, more terms?
No, I have not. You mean the epsilon function?
Yeah.
Yeah, I have not explained that, but we're working on it.
It's in the appendix.
No, it's not in the paper, it's a work in progress.
Oh, but you will have something like this?
Yes, so in this sense, this already, this tells us precisely where those corrections will come from. The leading divergence comes from this direction. And then what you need to do is you need to be able to consistently subtract this two-dimensional divergence without modifying these one-dimensional divergences. So the epsilon squared comes from here, and then 1 over epsilon convergence will come from here. And then all the rest will be epsilon to the 0 because it's fully finite.
How like, what would the graph theoretical description be? Like, the leading term here is about subdiagram and contractions.
Oh, it's the same description.
Oh.
So these rules that tell you about all divergences in every epsilon. But then you have to. The second step is to actually convert that to an actual integral. These coefficients of these things are going to be described in terms of integrals. And this is what we're working on.
Maybe
I have asked you in the past, but what is the connection between is there a polytopic interpretation of the solution of the Landau equations? So if you find the solution of the Landau equation, and so a singularity of the Feynman diagram,
Yes.
does it mean that something interesting is happening to this polytope?
That's a great question. In this talk, we assumed that all the coefficients in this F polynomial were positive. So in physics language, it means that we work in the Euclidean region. And this means that the divergences associated with Landau diagrams don't appear. In principle, you can still apply the same techniques even in the presence of the Landau singularities. Modular infrared issues. But in a sense, the story is kind of orthogonal. So you can study you can study the epsilon expansion, and you can study expansion around thresholds, Landau singularities separately.
I meant.
Modular infrared issues, in which case they might be infrared.
I guess I meant if there is a singularity in one of the coefficients of the epsilon expansion, doesn't mean something from the polytope, something like you're deleting a phase. I mean, some of the Mandelstam invariant is going to 0,
Yeah.
where you're eating a singularity. So the polynomial is being little bit less generic. So probably something is happening. I mean, you're dropping maybe some external vertex of the polytope, things like that.
Yes, something like that. We have not studied this exactly.
Well, but that's exactly what's happening. When the sum of the p-squareds go to 0, exactly what's happening is that some of the inequalities that define the polytope become stronger.
Exactly.
You're just chopping
So
extra.
you have to be you have to be careful whether you want to start with the original finite integral and generate some of the parameters, or you want to start with the situation in which the parameters are already set to 0. In principle, those things don't have to commute. So what Ivan was just mentioning is that we can just set it to 0. So set some of the corners here to be massless. And in this case, we know perfectly well how to apply it. It's governed by the same rules. The only thing is that for a given gamma will change whether you apply this rule or this rule. But there's a separate story in which you can also try to start with non-zero parameters and then take them to 0. And that we will not start.
If no other questions, then let's thank Sebastian again.
Really orthogonal to the line.